typos and such stuff. But thanks for correcting them. I really
Yeah,
appreciate it.
and thank you so much. Like now I'm able to converse well in the topics of measure theories.
Oh, great, great. Very glad to hear that. Yes, very good. So, do you also have measure theory courses at ISI Bangalore?
Not in BMath.
Yeah, I think so. Yeah. I think it's in MMath.
MMath.
MMath. Yeah. So, are you already in Bangalore, or is it reopened? Is that
No, it's online.
Oh, yeah, online. Oh, yeah. So you're studying from home?
Yes.
Very good. I mean, you're doing very well from home. So you're a very bright student.
Yes, thank you, sir.
Continue doing so, and you will go to places.
Yes, sir. Sir, actually, I wanted to ask you, like, is there any relation with complex analysis?
Yeah. So of course there is, and so first let me answer the question that you asked that I wasn't able to get back to and answer.
Yes.
So
Yes.
you
So
asked what are the next subjects to study, right, after this?
Yes.
Yeah. So first of all, the first thing that comes to mind is, of course, functional analysis, right? So we have done L1 spaces only in this course, and
yeah, Rias-Fisher theorem.
Sorry.
We have done Rias-Fisher theorem also.
Rias-Fisher theorem, yes. Yeah. So after that, the next logical step is to go to LP spaces. So now those are so for p greater than 2, it's those are Banach spaces. So you have to learn about Banach complete norm vector spaces. And for p equal to 2, it's a special case, and those are called Hilbert spaces, right? I think you already have heard. You might have heard.
Yes.
Yeah.
Complete inner product spaces.
Complete inner product space. Yes. So those are subjects on their own, right? And they are all part of what's called functional analysis. So, so the first logical course to take after this would be functional analysis, okay? Because that's the measure theory is lies in the heart of functional analysis. Okay, so that's one thing. The other thing is, of course, we have seen this Hardy-Littlewood inequalities, right? And
yes.
So these Hardy-Littlewood inequalities are used in what's called ergodic theory. And so ergodic theory is a sort of combination of measure theory and the subject of dynamical systems. So, so you want to study how some system evolves over time, and there the measure theoretic properties of those transformations. So those are usually some measurable transformations over a measure space. So say a map from, so you have a measure space X and you have a map T from X to X. Okay? And you want to know how this transformation behaves over time. So you take compose T with itself many times, and you want to see where your orbits lie and what are the measure of the orbits and so on. So that's part of what's called ergodic theory. Another part is which is closer. So I started with functional analysis. I went to ergodic theory, which is a little bit higher up. But again, something which is closer to measure theory is, of course, probability theory. So you can view probability theory as a sort of a special case of measure theory, but the theory is so rich in itself that it deserves its own study and it stands on its own. So probability theory, in fact, you will find a chapter on probability theory in Folland's book that I recommend. So there again, you have to, there again you have to think about convergence of a sequence of measures. So I didn't cover this topic. So you have a sequence of measures, and you need to find a way to talk about the convergence of measures. And so the central limit theorem is one of the basic results in this chapter. So that's immediately accessible to you. It won't be that hard to study for you. And so that just covers the basics of probability theory. So then after this, of course, there are many problems, many areas in probability, like stochastic differential equations, where you are really concerned about the change of measure. So I also didn't cover this. So it's called the Lebesgue-Radon-Nikodym theorem, which allows you to
I think
move from
like other than positive measures, non-negative
for
measures.
complex valued measures. So I didn't get time to cover it in this course, but it's again very close to what I did. So if you read it on your own, I'm sure you will be able to understand. So I think this Lebesgue-Radon-Nikodym theorem is also covered in Folland's book, but it's not covered in the book I recommended by Terence Tao. So there is yet another book by Terence Tao on measure theory.
An epsilon of room.
Very, very good. Yeah, an epsilon of room. So it's covered there. This Lebesgue-Radon-Nikodym theorem. So this theorem is used widely in stochastic differential equations, and in turn, because it's probability statistics, this is applicable to a wide variety of subjects. So somebody asks, what are the applications of measure theory in economics, physics, and so on. So wherever you have differential equations, wherever you have some sort of probability, random variables, and stochastic processes, so there it will be useful. It's not as direct in the sense that you won't be able to get in touch with measure theoretic concept directly, but it's always behind. It's a sort of a platform for probability theory
as a base.
As a base, yes, exactly, as a base, because all the concepts are measure theoretic, but then there are various other notions that you don't deal with in measure theory that come up in probability theory. So the concept of Markov processes and martingales and so on, and those involve measure theory in the background. So all of these stochastic processes are random variables, which means that they are measurable functions. Okay, so that's the very basic definition of a random variable. It's a measurable function from a measure space to some scalar valued function like C or R, usually R. Okay, so so these are first function analysis, then probability theory. These two are closest to what we did in the course. Then ergodic theory, and of course stochastic processes. It comes, I'm putting it inside my probability theory. But then also you have the course on harmonic analysis. You can also go in that direction. And harmonic analysis
that needs functional analysis.
That does need, that it's heavily dependent on function analysis, especially L2 spaces. So that's about Fourier. It's like a Fourier analysis on groups. Okay, so your harmonic analysis in one sentence can be mentioned like that. So Cauchy-Rel formulas. So if you have heard about Fourier analysis, there is a Cauchy-Rel formula.
No, I haven't.
Yeah. So.
Like Fourier analysis needs measure theory. Is it like that?
Of course. It's at the basis. So function analysis, wherever you look at it.
Okay, so it's like function analysis and then Fourier
yes,
analysis and then harmonic analysis.
Yes. So Fourier analysis by if you just say Fourier analysis, it's usually meant on Euclidean spaces. And if you say harmonic analysis, then that means you're also considering some groups, so topological groups. Okay, so you put some measure. So we discussed about Haar measures, right? We give some examples of Haar measures. So those are measures on groups, and harmonic analysis deals with generalized Fourier analysis on groups.
Okay, sir.
Yeah. And of course, in complex analysis, you can use basically all the available techniques that we used. But also, for example, what I wasn't able to discuss in this course was about Hausdorff dimensions and Hausdorff measures. And
yeah, it was extra content.
it was extra content, but I wasn't able to actually do it in the course. So
okay.
yeah, so when you
I
have
think
this,
Stein and Sakarchi has a chapter on
Stein
it.
and,
I think.
yes, it's at the end.
So like, what is the setting? Like, how
the setting is it's about having. You may have heard of fractals, right? So there is this concept of self-similar structures.
Yeah.
And what the idea for Hausdorff measures is that if you have, say, a line in R2, then it will have Lebesgue measure 0, so right. So, but there are objects within R2 or Rn which have dimension strictly greater than 1 and strictly less than 2. Okay, so somewhere in between. And so the Hausdorff measure tries to capture information about those objects, like the Koch curve or the Cantor set. So even for the Cantor set, you will have some non-trivial Hausdorff dimension, which is greater than 0 and less than 1. Okay. So it's log 2 by log 2.
Okay.
So these are the concepts of the Hausdorff dimension. When we think of dimension, it's usually a natural number, right? But when you talk about the Hausdorff measure and the Hausdorff dimension, then it could be a real value, positive real number as well. So it's a more generalized notion of dimension. So the idea of Hausdorff measures is to capture the measure theoretic concept, the measure theoretic information of objects like the Cantor set, so fractal-like objects. And in complex analysis, there is this Mandelbrot set, which gives you a fractal, and you would like to use measure theory to know what is the dimension of that set. So this is used very widely. Although it's not.
This comes under like.
It comes under holomorphic dynamics. Okay, so. It's
fractal geometry.
Fractal geometry, yeah. So,
okay.
Do you know about this YouTube channel called 3 Blue 1 Brown?
Yes.
So he has a recent video on the fractal like objects in the Fatou sets and Julia sets. And
okay, then I'll watch it.
Just check it out. It's very interesting. So. So the measure theory comes in when you want to talk about the dimension of fractals, for example. Okay. So I wouldn't say it's a main part of complex analysis, but it's definitely an interesting subject on its own. And other than that, of course, there are other ways you can put measures on subsets of the complex plane. And I forgot the construction now, but so there is a way to put a measure on the boundary of a complex domain using some techniques. I forgot the construction now, but maybe I can put a link about it in the discussion forum where you can check it out. So okay, that's also a possibility. Yeah, so it is used in study of harmonic functions. It's called the harmonic measure, but I forgot the construction. Exactly.
If we are reading more advanced topics of measure theory, then where to start? Like which book?
More advanced, of course. So there are various pathways you can pursue. So one, as I said, is functional analysis. You will find plenty of books on it.
Like which one do you recommend for functional analysis?
I would recommend Analysis Now by Gert Pedersen. Maybe I can write it down. Let me share my screen. I'll write it down so that you can copy it. So analysis. Let's say a different scale. So analysis now by Dirk Peterson. So it contains all the basic stuff about Banach spaces, Hilbert spaces, and so on. Some operator algebra as well. So this will find Banach spaces, Hilbert spaces, operator algebras. The basic stuff. Okay? Nothing fancy, but I think at this level it's enough for you.
Okay, sir.
But it's not a very extensive book, but it's a good place to start. Another book is it's called Banach Algebra Techniques. It's probably in functional analysis. So this is a book by Ronald Douglas. Okay. And it's also very beginner friendly. So it starts out from scratch. It's not too extensive so as to become boring. And it's not a very big book. So neither of them are very big books, but they cover very well the basic material on these topics. So I would say the first one is more basic than the second one, but they're both good. And this is of course on functional analysis. But then if you want to study more measure theory per se, not go to functional analysis, but just measure theory. So then there is the option of studying more geometric measure theory. And I think there are only one or two books which are well known. I forgot the author's name, unfortunately. Wilson, I think. I'm not sure. But I'll check and let you know. And so this geometric measure theory is about, we did some stuff on the big points of density. And so we want to know how condensed points are with respect to some measure. And the geometric measure theory tries to deal with such problems. So that's another.
Okay, sir.
Yeah, that's another way to go. So these two, the functional analysis stuff is more standard. Geometric measure theory is not covered usually in most graduate schools. But of course, this is quite from the material that we had. This is quite accessible for you, okay, from the course material that we've already covered. So it's not too high, too advanced. What else? So probability theory, of course, a good place to start is Fallen. So start with Fallen. And right now I can't think of a good open. Just probability theory, which is sort of math oriented. I have to think about it. So, I'll try to fill in these question marks for you in the discussion forum. Okay.
Okay, sir.
Yeah. Any other questions that I can help you with? Sagar, hi.
Good evening, sir.
Hi, how are you? Where are you
Yeah.
based?
So I'm from Haryana.
From Haryana. And which university are you going to?
NIT Surat.
NITs. Okay. Good. Very good. So you're attending now the institute is reopened, or is you're still having online stuff?
So online, they told us to that it might be open in January.
In January.
Let's hope.
You said NIT Surat.
Yes.
Oh,
SVNIT, Sardar Vallabhbhai National Institute of
okay.
Technology.
Okay.
So first of all, your course was suggested by one of my senior. He took the course last year,
Okay.
and I really loved your course. How you
That's very good.
start with the intuition, build the
Yeah.
theorems and
Yeah. So my idea was, so usually if you look at measure theory courses, the one approach is to go to just start with the abstract things like definition of a sigma algebra, definition of an outer measure, and then give examples of those things. So that's a top-down approach. So you start with the abstract stuff and then go down and see examples. But this way, which is it's not mine, but it's the Terence Tao's presentation of measure theory, and I thought this was more intuition based, and it's a bottom-up approach where you start with the very rudimentary idea of a measure, what it should be, and then you start building up the theory, and eventually land up at the Lebesgue measure, and then you kind of study the abstract stuff. So by the time you're studying the abstract stuff, you already know a lot of examples and how things work. So both approaches have their pros and cons, I would say, and it's a matter of taste, who likes what. But I'm glad you like it.
So I need a little advice from you.
Yeah, tell me.
I want to work in the field of low-dimensional topology. And when I start with the topology, general topology, I always say this capital LP spaces and all that. I know this small LP spaces and I know L2 spaces from the context of metric spaces, but I never understand this capital LP, capital L, capital LP spaces.
No, but where did you study LP spaces in low-dimensional topology?
Not in a low-dimensional. Last year I took a course of function analysis.
Okay, yeah. I was just telling Aprameh that so the first, the next step would be after this course would be to take up function analysis, which has all these LP space stuff, so Banach spaces and Hilbert spaces.
So actually, sir, because of the college curriculum, they put the function analysis in the fourth, in the like a 2 semester before measure theory.
Oh, that's bad. Yeah.
That's actually a disadvantage.
Yeah. So because like I said, measure theory lies at the basis. It's at the bottom of function analysis, and unless you know what L2 means, what L1 means, and what LP means, it's you can study it abstractly, but then you will not have examples. You won't be able to understand the examples, the most prominent examples of Banach spaces and Hilbert spaces.
So, sir,
thank you, Aprameh. If you want to leave, you can. Thank you for coming.
Thank you, sir. So if I have any more questions, I'll mail you.
Of course. After the course gets over, I won't be checking the discussion forum so often. So it might be better to send me an email on my
IMSc mail.
Yeah. Okay. So it's just Indrava at imsc.res.in.
Yes, sir.
Maybe I can
Thank you.
Maybe I can write it down. Sorry, Sagar, I'll just come back to your question. Yeah, so you can write to me at this email address, and that way I'll reply to you.
Bye, sir.
Bye. Yeah, tell me, Sagar.
Sir, like after studying topology, what should I now learn to go for the field of the low dimensional topology?
Yeah, so what have you learned in topology?
That's just the general topology
General
compactness.
topology stuff.
Yes,
Okay,
yes.
so the next step would be to learn about algebraic topology. Okay, so the low dimensional topology usually deals with fundamental groups, right? So that's part of algebraic topology. So if you look at say Munch's book, you will find material on algebraic topology as well. And then so I'll just write it down. Algebraic topology. So part 2 of Munch's. You know this book by James Munch?
Yeah. Yes, yes, sir. I'm following this one only.
Yeah, James Munch. And then there is a nice book by Alan Hatcher. With the same name, Algebraic Topology, and this is available online for free. Okay. So you can check out these two books. So I would recommend start with Munch's and then study Hatcher. Okay. So here in Munch's you will find. Let me write color. So here you will find first fundamental group. So the notions of homotopy. Okay. Homotopy. So this algebraic topology stuff is based on the notion of homotopy, and in the second book you will find homology. Okay. So what they do is to so what is algebraic topology do? It takes a topological space and gives you an abelian group. Okay. So the basic question in algebraic topology is to ask when two topological spaces are homeomorphic or when they are homotopy. Okay. So the idea is to look at their corresponding abelian groups, and that gives information, not always, but that gives you some information about whether they are homotopic or not. Okay. So if two topological spaces are homotopically equivalent, then their corresponding abelian groups. So this is the fundamental group that I was talking about. Fundamental group. They are going to be isomorphic. Okay. So that's the basic concept. And so you can classify, you will find a classification of two-dimensional surfaces in terms of the first fundamental groups. So it's also a very powerful tool, but it doesn't stop there. When you study low dimensional, if you want to study low dimensional topology, you will have to go to higher homotopy groups, and that requires some work. Okay? It's not very trivial, and in fact, even some basic questions are still open in that. So higher homotopy groups, I think is covered in Alan Hatcher, but I'm not totally sure. And homology is yet another way to, it's different from the idea of homotopy, but it's yet another way to assign an abelian group to a topological space. Okay? And the homology groups are somewhat easier to compute. And so whenever you study low dimensional topology, you'll always have to deal with homology groups and homotopy, higher homotopy groups. Okay? More homology than homotopy, I would say, but yeah, I'm not an expert in this subject, but I mean, both are very important. So these two places are a good place to start. And of course, just search for low dimensional topology lecture notes. You will find it online. There are plenty of resources online on low-dimensional topology. There are blogs or lecture notes and websites dedicated to such things and so on. So you'll find plenty of material online for low-dimensional topology. But you have to start with the basic stuff of algebraic topology. So advanced material would also cover some category theory. And homological algebra. So these two are also somewhat important in low-dimensional topology. Does that answer your question?
Sir, it is, but I actually have one more doubt.
Yeah.
Like when we are talking about low-dimensional topology, so we restrict ourselves to the low dimension, like 1, 2, 3,
Yeah,
or maybe
up
4.
to 4, I guess. Yeah.
Up to 4. And there is also one thing as a node theory, how we study nodes in topological spaces, and that restrict ourselves to the 3 dimension, if I'm not wrong.
Yes.
So is the node theory is a part of the low dimensional topology, or is just
it's I would say it is a independent subject, but it can be considered low dimensional topology because you're using topological tools to study 3-dimensional objects. So it can be considered part of low dimensional topology, but it's an independent subject on its own. But yeah, that's a good remark actually. So I would say node theory also is interested in this. I would add it also as part of low dimensional topology, but it's not all of low dimensional topology. So there are many other things that one can do.
And these basic things like manifold, the space-time 4-dimensional manifold, they all cover in this low dimensional.
No, space-time. If you want to study Minkowski space, that's a bit different because then you have to consider the geometry.
Oh.
So then you have to consider, so there is this bilinear forms, and there's Riemann tensors and so on. So there's a concept of a Riemannian metric and a pseudo Riemannian metric, and so that's part of more part of geometry. But in a sense, you're right because nowadays, there is a lot of interaction between topology and geometry. So it's not that they are sitting in different corners of the room. There's a lot of interaction, and of course, a lot of geometric ideas are applicable to low-dimensional topology, especially surgery theory. I should add surgery theory. So all these things are not completely devoid of geometry. Surgery theory, for example, if you're talking about surgery of smooth manifolds, okay, that's a little bit easier than surgery of topological manifolds, and then you have to consider the geometry. So yeah, so it's not all topologies. There is definitely some geometry.
So now coming back to the major theory, actually I have one doubt in the whole course. In 0 to 1 real life, we find that the measure of rational numbers would be 0.
Right.
Okay, so when we find the probability of finding a rational number in between 0 to 1, that means there would be 0. But we can always find a rational number between 0 to 1, 1 by 2, let's say.
Yeah. So that's the thing about measures, a vague measure at least. Like I was telling Apramya earlier. So if you want to have information about things that are not quite in the continuum, in the sense of the real line, it's not continuous in the real line, like the Cantor set, for example. Right?
Okay.
But if you consider the Lebesgue measure, you just get 0, right? So then one should rather consider Hausdorff measures and the Hausdorff dimension of such things. But even so, the probability question is still going to give you 0. So that's how, but that's how it's defined. So if you consider the probability of finding a point in a line, it's always going to be 0, unless it's a Dirac measure. But that's a specific probability measure. That's not that used that widely. But otherwise, if you have a continuous measure, so like a diffuse measure, then it's going to give you 0. But that's how it plays out.
So it is some sort of it is like a drawback how we define the measure.
It is, yes. So that's what. So that drawback of studying objects which are not quite discrete. So it's not like one point, but somewhere in between. So the Cantor set, for example, is an uncountable set, right?
Mm-hmm.
So, but it's still not continuous. It's all points are isolated, right? So
yes.
So to study those objects in a measure theoretic way, you need Hausdorff measures rather than Lebesgue measures.
So in week 5, you have mentioned about that extra will be Hausdorff measure and all that.
Yeah, I'm sorry. I thought I would be able to cover that, but I didn't get time. Because, even last year I didn't get time. I should have removed it this year, but I forgot.
So I go through that full-length book.
Yeah.
Is there any source to learn this Hausdorff measure and all this?
Yeah, it's there in Follen's book.
There's just the definitions, I guess.
Okay. There is another book, but I'll write it in the discussion forum. Okay, I don't remember the name of the author, neither the title, but it's a good book to learn. So Hausdorff measures, the one I wrote before. Yeah, it also falls under this geometric measure theory thing. This a little bit advanced, so you can already talk about Hausdorff measures in a more elementary way. And I think even the book of Stein and Shakarchi has Hausdorff measures. Yeah, I'm sure it has it. So you can check out this book of Stein and Shakarchi. Okay, you will find. So I agree that it's not very well done, very extensively done in Follen. In Stein and Shakarchi, especially when they consider the fractal self-similar sets, I think one of the chapters at the end of the book, and you will find some material there for Hausdorff measures.
Okay. So do we get to like more courses from you in the upcoming years? Yes,
I'm teaching a general topology course, but that's not for master's students. That's more for undergraduate students next semester. That would be an NPTM. That's the only one planned until now.
Anyways, if I get any query, I will mail you to.
Of course, anytime. Yeah.
Okay. Thank you very much, sir.
Thank you, Sagar, for joining. Yeah. Komati, if there is no one else, we can stop. Anyone from NPTEL?